All right, thank you, Ben, and good morning, everyone. Happy to be here. Thanks to the Energy Exemplar team and all of you for showing up bright and early after all the events last night, and we're looking forward to spending a little bit of time walking through some of our observations on evaluating costs and risks in a resource planning environment, particularly around some of the emerging technologies that we heard a lot about yesterday. So before getting into the meat of the presentation here, I just want to give a quick overview of who we are. Clare and I work for Charles River Associates. We're a consulting firm of about 800 folks total, focused on economic consulting. Primarily, our group is in the Boston and DC offices. We have an energy practice that has about 50 to 60 people, and we have several different practice areas within that energy group. One of them is focused on utility strategy, investment planning, and resource planning, and that's what Clare and I do a lot of our work on, as well as Parag and Jonathan, a couple of our colleagues that some of you may have met over the last couple days. So within that group, over the last 18 months or so, we have worked with utilities in about 15 states of the U.S. on a variety of different resource planning issues shown up here on the slide. And what we're going to do today is walk through some of the emerging trends that we've seen and really focus on a practical case study and how we've been looking at some of these trends within Aurora. So a lot of those utilities that we have been working with most recently have identified several emerging challenges. We heard a lot of them come up in various forms in the presentations yesterday, so I think it's a common theme that most of the group here will recognize and understand. But as we think about where those resource challenges are and what the modeling challenges in evaluating those planning issues are, we've kind of split them down into three categories, and we're going to touch on a lot of these in the next couple of slides. So number one, I think a trend that's obvious is that the risks and uncertainties in power market modeling and utility resource planning are broadening and growing. So as opposed to a traditional view on average power price and gas price and carbon regulation trajectories, we're seeing a lot more interest in understanding the risks around granular power price uncertainty. And in addition to those commodity and regulatory pressures, a lot of interest in understanding renewable resource output uncertainty. So dispatch is no longer just a merit order economic question, but we really care about the availability of resources that are intermittent. And combined with that, a lot of market design changes that are underway. So folks here in this room operate in a lot of different regions and markets, but we're observing a lot of our clients interested in how the markets are changing, whether it's from a reliability, capacity market, energy and ancillary service market perspective, and how the different resources and emerging technologies can respond. So the modeling challenges there are obviously incorporating more price risk at a granular level, and we'll talk about that in this presentation. Incorporating renewable output at a very granular level and the uncertainty in that, and we'll touch on that as well. Number two, technology is rapidly changing. Again, we heard a lot about this from different perspectives yesterday. Storage is on the radar of many resource planners and those in the sector. And we're looking at unique applications of that, whether different types, storage duration, pairing renewables with storage, and how that might even come behind the meter and change customer behavior. And in order to address that in the modeling framework, we, of course, need to evaluate storage dispatch under different operating models. And we'll talk about that a little bit in a couple slides here. And also assess how that may be changing not only from things that utilities and planners can control, but things out of your control when it comes to customer behavior. And then finally, as I hinted at a minute ago on the market design change topic, generation resource value is broader than the traditional energy and capacity view that has typically been undertaken. So in addition to that value, there's ancillary services value. There's potential transmission and distribution, upgrade offset value, and as we think about resource planning challenges, we're looking at how to incorporate some of that in the decision-making framework. So overall, I think these are kind of a couple of key baskets of risks and planning uncertainties and issues that are coming up. And what we thought we would do today is take these and try to distill them down into a little mini case study that we've developed to go through an evaluation within the Aurora tool and some other companion tools to look at how some of our utility clients are evaluating these risks and how we are trying to incorporate some of the uncertainties and modeling challenges into some opportunities to look at those risk trade-offs. So at this point, I'll turn it over to Clare to start walking through a little case study that we've developed, and we'll go through some applications of looking at these modeling inputs from a risk perspective, and then give an assessment on how those risks and cost trade-offs might be playing out for certain technologies. So Clare, take it away from here.
Thank you. So as Pat mentioned, I work with him closely in the DC office, so I'm going to walk through sort of the setup of our case study and some of the inputs we used, as well as the Aurora functions that we used, and then we'll walk through the results. So the first risk that we layered in, as Pat mentioned, is price risk. So we looked at power and gas price risk. If you look on the bottom there, those green lines are sort of the fundamental forecasts that we use. So we use Aurora's long-term capacity expansion functionality to develop long-term power price forecasts, fundamental forecasts for a base case. And then what we did to layer in power price risk and gas price risk was use a stochastic model to develop hundreds of risk simulations around that base case. So the gray lines there are those risk simulations. So gas price, we generally do this on a daily basis, so you can see that on the bottom left. And power prices, we incorporate risk on an hourly basis, which you can see on the right. This is a representative zone in MISO, so you can see the historical data there. We use that zone just because that's where we've been working a lot recently, but I think there are probably zones where you would see even more of that volatility coming in, including downward volatility. This is generally see more upward price spikes because of gas, so that's sort of the power and gas price inputs we're using. And I'll walk through later, but we use a script to run these through Aurora as inputs. So the next risk that we're layering in is renewable generation. So you guys are all Aurora users. You know that generally renewables are shaped on a monthly basis with the typical week vectors, but we wanted to layer in some additional granularity there. So what we did was took 3 sites in our sample MISO zone, and we got solar irradiation data, so that's the amount of solar that's reaching the ground. We got snow coverage data, and then we used the PVSys software to see how that would impact solar output. So here you can see sort of what those different days looked like, and we randomly sampled each of those days based on actual data to create 5 20-year hourly vectors, and obviously using the time series hourly table, so we're replacing those weekly vectors with the hourly vectors. And you can see here that we're getting into the risk of maybe some snow coverage. It looks like there's a day in January where there's basically no solar output, maybe 1 hour. July is a little bit more consistent, but there's still some days where there's cloud coverage and that sort of thing impacting solar output. So it's not quite a smooth shape. There's some randomness there. So to walk through the Aurora setup, I wanted to walk through some of the tools that we've been using a lot in our analysis. So the multiple time series hourly table function is something we've used a lot when you're talking about 20-year hourly forecasts. That turns out to be a lot of data, especially if you have 100 power price simulations. So just as a data management tool, that's something that we use quite often to manage that. We also use the portfolio function a lot. So we are running, in this case, Aurora using an input price, which means that we can set up dozens of portfolios if we want to and test them all at once, because we're kind of making a simplifying assumption that the portfolio is a price taker and operating in this market that we've already sort of fundamentally modeled in the past. And then we also have a script. So on the bottom right, that's sort of what the script looks like. I worked very closely with Paul Sony, who I don't think is here, but with Energy Exemplar, to create this script, and it changes three things: the gas price reference vector, the power price reference vector, and the run ID. So when you look at your output, you have 100 different run IDs, and each one has a different power and gas price iteration that was used. So for the case study, we set up some different portfolios just to give you a window into how we would sort of think about looking at a utility that needs to replace some capacity and how we might kind of stress test those different options. So very simplified, we used a 100 megawatt portfolio, peak load, and gave it sort of a average demand shape. I mentioned we're in MISO, so we used an 8% reserve margin that they're planning to, and we're allowing unlimited market purchases and sales. So their resources are operating in the market, and if they have a shortage, then they're going to buy at the market price, and if they have excess energy, they're going to sell. So bit of a simplified assumption. There's also a few resource assumptions you can see we made. 40% solar peak credit, obviously subject to change. There might be some seasonal variation there, but that was the assumption we used. The random solar shapes, they don't come out exactly the same every single year, but they're all within about 23 to 26%. We also use 4-hour storage and 87.5% round trip efficiency for that storage. So we have 5 portfolios, solar only. We have 4-to-1 paired solar plus storage, 2-to-1 paired solar plus storage, piece of a gas CC, and then a solar plus peaker. And Pat is going to walk through what the different risk profiles for these portfolios look like.
Yeah, so as Claire mentioned, I think the objective here was really to get a sample. Obviously, if you're looking at a real utility portfolio, the portfolio is more complex. So you know, the results that we'll walk through here are very much illustrative for a case study. Your actual portfolio may have some other existing gas or coal or wind or any number of other resources. But the idea here was for a client of ours, which we've adopted in this little case study, to assess incremental changes in the portfolio and how adding these different resource options, which were their incremental options, solar, storage, and different gas technologies, how that would look on the cost and risk profile. So, you know, very much illustrative here, recognizing that real portfolios are a little more complex. So before I touch on what some of the key results findings are, just a few more assumptions for clarity on this case study, and obviously there are risks and uncertainties on several of these items that you may be interested in testing, whether it be from a cost perspective or some of the other commodity price forecasts and uncertainties that Clare laid out. But from a portfolio assumptions point of view, this particular case study was assuming additions of solar or gas in 2020, and the cost profiles that we've got there on dollar per kW basis are over to the right. So that would be pre-tax credit for the solar resources, $1,200 kW type planning number. For storage, the idea was that we could be waiting a bit and potentially pair the storage resources as the costs come down. And we're using the NREL low case in this particular case study for what storage would cost on a dollar per kW basis. As Claire mentioned, in this little case study, we're assuming 4-hour duration storage only. So those were the capital cost estimates. As Claire mentioned, we set up the portfolio framework within Aurora. So several users here, I'm sure, are familiar with that. And within that framework, we were focused exclusively on the variable costs and the production costs across the different stochastic iterations. So in this case study, we have 100 runs that are going through for different hourly power prices, different daily gas prices, and those different hourly solar shapes all combined together. So on top of that, we have a separate financial module. So I know some users, incorporate the financial metrics in some fashion within Aurora. We have a slightly different revenue requirement tool that we put on the back end. So all those capital costs are going to be assessed in a revenue requirement framework as a utility may invest and get a return on their asset, or have a debt repayment schedule in the case of a muni entity, for instance. So in addition to that, as I mentioned at the outset, the other revenue streams that we're considering in addition to energy and capacity are also important, and we've got a little note on the bottom right about some of the planning assumptions there that we've used. So we've been looking at ancillary service value in Aurora and in some other tools that look at some historical values, and for this case study, we're using a couple of expected value type planning assumptions, and you can see that the storage resources we feel have greater value in this particular MISO market, and then as you step down to a flexible advanced gas peaker and then a combined cycle, a little bit less value. So for planning purposes over this study period, we're just using those dollar per kW value drivers in our financial model. So what we've got here is 100 iterations of dispatch and costing, and we're layering on a revenue requirement and ultimately doing a levelized dollar per megawatt hour cost for this portfolio. So again, I'll emphasize that it's from a portfolio perspective, and as Clare mentioned a couple times, we've got full dynamic interchange with the market. So in addition to the costs of either building and operating these different resource options, anytime the option's not available, there's an ability to transact, in this case with the MISO market, and Claire's going to show a couple hourly examples of how that works in a minute. So when we roll all that together, what we find here is a couple different views of the costs and risks associated with these different resource options. So the top graphic, we're showing the expected cost, basically the average levelized NPV over a 20-year planning horizon for these different portfolios that Clare outlined on the last slide on the x-axis. And then on the y-axis, a measure of risk. We're taking a simple standard deviation of these iterations. Sometimes we've looked at an interquartile range between the 25th and 75th percentiles, or some tail ranges or other measures of risk. But ultimately, what a planner is generally going to look for here is to be in the bottom left-hand corner of that graphic, a portfolio that is providing low cost and mitigating risk. And overall, over that 20-year period in this hypothetical buildup, what we're seeing is the solar-only portfolio has the lowest cost, probably not a surprise given where we see solar prices and the lack of variable costs once the resource is in the ground. And in this particular simulation over the long term, actually a pretty low risk profile. Now that was dependent on an ability to transact within the market and in a relatively low market price environment now, although over time, as you saw from an earlier slide, we have increasing expectations for market prices that may or may not come to pass, so keep that in mind. We see that the gas combined cycle, just standalone combined cycle in this instance, is higher cost over this 20-year planning period, also has a little bit more risk as a result of dispatch uncertainty, gas price risk that exposes that portfolio option to some uncertainty. And then in the middle, we see some trade-offs between the solar plus peaker option and the solar plus storage option, generally with the storage pairing resources showing a lower cost and a lower risk profile, given the assumptions that we've made here. Now, one thing that we did on the bottom here is zoom in a bit more on a 10-year outlook. So instead of looking over this entire period, what if we look at a shorter duration, don't allow for that significant run-up in power prices that we might expect over the long term with potential gas price or carbon pressure, and focus more on a shorter duration period where we do not have a lot of that energy value for a standalone solar resource. And when we zoomed in on that 10-year period, we see some more interesting conclusions, I think. Where we see a bit more of a trade-off that may be developing between a standalone storage resource and one that integrates storage. Standalone solar, and one that integrates storage. And I think this is kind of a key question that a lot of our clients are trying to understand now. If we're integrating more storage, is there a risk mitigation thesis or expectation that we can evaluate? And Claire's going to walk through on a couple slides why this is. But if you look at the bottom graphic, what we're showing there is the distribution of levelized NPV cost profiles over those 100 iterations for these three different options. So the bars, if you look at the shaded bars, they measure the 25th percentile to the 75th percentile with the median in the middle. And then the tails or the whiskers up and down are showing the range up to the 95th and the 5th percentile. So over that 10-year period, you can see that the solar only resource has a broader distribution than one that starts integrating storage. So we're getting at the risk mitigation benefits that could materialize if you have cost-attractive storage resources to pair. And the reason for that is you limit the exposure to power price volatility. If you're exposed in the market with a lot of solar and having to purchase power to meet your portfolio's needs and the prices are spiking, that's risky. If you have a day with cloud cover coming in the afternoon and don't have a way to back that up and get exposed to a market price, that may also be risky. So what we see here is as you add more and more storage, equivalent capacity rating, less energy in total, but more storage to mitigate against those risks, although the expected cost, if you see those boxes kind of going up a little bit, the middle lines over time, from left to right, although that expected cost increases, the width or the height of those boxes is showing some decrease. And at the 95th percentile, we're even seeing the paired solar plus storage options mitigating a bit of that worst case risk versus standalone solar. So an interesting outcome, obviously dependent on a lot of these different assumptions that are moving around, but one that we found quite interesting and one that some of our clients are starting to look at in more detail. And what's the right pairing ratio? What's the right cost trigger that would result in this type of outcome? And of course, what is the future power price volatility going to look like, which is also going to dictate things. So I'll turn it back to Claire to kind of walk through a couple of interesting hourly profiles that give you a sense of what's going on before we close here.
Sure. So I thought it'd be interesting to briefly look at the hourly outputs, especially because we're layering in that sort of random hourly solar shapes. So it's kind of interesting to see how the paired storage reacts to that. And obviously the paired renewables and storage is something that Energy Exemplar has been working on a lot. So we have a couple graphs here that basically compare those three different solar and storage portfolios. There's two axes. So that orange line is based on the right axis. That's the power price. I would pay a little more attention to the shape than the actual value. And then that dotted line there is demand. And those two shades of blue are the solar and storage. We are pairing the storage and shaping it based on price. So that is basically exactly what you see here. So kind of interestingly, you see storage charging in the morning and a little bit later in the day, in the afternoon. And then it's outputting sort of in the evening peak price spike. And this is a winter day. So that is sort of what you see there. And then in the 2-to-1, it's kind of interesting. You can see they're almost, this utility is able to almost completely meet its load during those peak hours. So sort of a high potential to reduce your exposure to price spikes, specifically later in the day with the storage, especially when you have that higher pairing ratio. But potentially not enough to outweigh the additional cost of the storage. So this slide is the summer day. Fairly similar thing, although we're seeing the charging happening only in the morning, and looks like it's outputting a little bit earlier in the afternoon as it hits that sort of afternoon price spike. Yeah, and they're a little bit more exposed on the load, it looks like, in the summer afternoon. So even with the 2-to-1, just based on their load profile, still a little bit of price risk exposure there. So potentially would need even more storage if they wanted to be able to fully cover their load on a hot summer afternoon. So Pat is going to walk through some conclusions.
All right, thanks. So I think to wrap up, a trend that we're observing right now, and I think many of you are as well, and it came out in some of the presentations yesterday, is that standalone solar, just looking at it on its face, is emerging as the lowest cost energy option, at least, going forward. When you look at LCOE, admittedly not a complete metric, but projections of that versus the other alternatives are continuing to have that resource type bubble up, and we're seeing a lot of solar showing up in resource plans going forward, and we expect that to be the case for a lot of our clients and others across the industry over the next several years. But as many planners in the room will attest to, this is not the only metric that needs to be considered, and I think what we've tried to illustrate here is that there are elements of risk and reliability that need to be considered as well, and many other things that are on the table. So it spans the gamut from the cost uncertainty, what are the costs of solar and storage technologies going to look like, how should we look at that under scenario expectations, what are the tax credit considerations when you're pairing solar and storage versus unpairing, and what does that look like and how does that impact this framework? Secondly, what are the market price expectations looking like? Not only the broad price expectations on will gas go to $3, $4, or $5, or will it stay at $2 to $3, but also that granular volatility, which really matters more and more as a portfolio may be more exposed to market uncertainty if it's relying on more intermittent resources, as well as rules evolution. So we're observing with a lot of our MISO clients recently that there may be a push to a seasonal resource adequacy program that would not just rely on summer peak, but also look at different seasons, including the winter, where some of these solar exposure questions come up. And then finally, some of your other sustainability or carbon emission drivers that are on the table. So a lot of what we're observing and working through with our clients is a multidimensional perspective when it comes to cost and rate stability and some of these flexibility metrics around commitments and ability to respond to market rules changes, as well as diversity and sustainability metrics. So hopefully we've given some insight on how to look at a couple of those first two on cost and rate stability and how the emerging technologies are playing into that. And I think we've got a few minutes here and happy to take any questions or comments.
Thanks. We do have a few. So, thank you, Pat and Claire. First question is one that's regarding the solar output on one of the graphs that you showed. So it says on the graph, what is being done in the model with the solar output that's over and above demand? Does that make sense?
Right. Yeah, so that's being sold into the market. We're assuming full interaction there.
There was another question about solar peak credit assumptions, and just if you could share any insight into, I think, your choice of 40%, how you derived that assumption, or other thoughts on how to come up with an appropriate solar peak credit for different scenarios.
Yeah, I think that was for a planning purpose for this little case study. I think it's kind of in the middle of what we're seeing now. If you look across the country, you may have areas with low solar penetration, still getting 50, 60 plus % right now. But as that number of solar megawatts on the system grows, we're seeing a movement lower. So this was kind of an average view of what it might look like in the near term. As I mentioned at the end there, if we're shifting to more seasonal constructs over time, that's going to be a variable that's not only a single year planning perspective, but you could get a lot of credit in the summer, you could get hardly any in the winter, depending on your load profile. That could really matter. And there's also risk of that credit going down. So you might build out now where it's 50%, but in 10 years it'll be 30%. So very important uncertainty. We kind of just used a middle of the road number for this little illustration, but certainly a variable that's going to change.
Yeah. Great, thanks. A couple others. One was just in terms of sources for market prices. So I know you used the input prices function for this one. Did you develop your own power price curve in the models before that and then plug that in for the portfolio runs, or did you use
exactly.
other? Okay.
So a lot of what we've been doing recently is, doing those long-term capacity expansion and a few scenarios and creating an hourly price forecast and then turning around and using that as an input just to give us a little bit more flexibility on analyzing portfolios, and from a run speed perspective, much faster if you're using an input price. So that's part of the reasoning there.
Yeah, nice to be able to do both. Mm-hmm. Okay. Let's see here. A few others, they keep coming in. Hot topics. Let's see if we can take one more at least. There was a question about what is the difference between the 2-to-1 versus the 4-to-1 solar plus storage. Do you mind just elaborating on that a little bit?
Sure. So we're trying to keep them equal on a UCAP basis. So it basically means we're paring back the amount of solar and then adding, basically, on a nameplate basis, 25% of the solar capacity as storage, and leveling that out on the UCAP so it meets that 8% reserve margin.
Yeah.
So for the 2-to-1, you would see less solar, more storage. Yeah.
Okay, great. I know there's a few others. Please get with these guys afterwards if you don't mind, and I know that they'd be happy to chat with you some more, but let's give them a hand for their presentation. Thanks.